We'll review today chapter, let me get my pen. We'll review today chapter 3, the power or diode rectifiers. Again, this is for course EL4242, power electronics. Before you go further, we look through the full wave rectifier, we look through the theory. We know that full wave rectifier, this is this is not a bridge one, this is like the transformer. During the positive half cycle of this input voltage, this is the input voltage, the diode conduct, and then the negative half cycle, the diode due to conduct. Now the output voltage is like a 2 half sine wave, twice that one, and if you do the average of this waveform, this will come 2 Vm by pi, 2 Vm by pi. This is the average voltage. What will be the RMS voltage? RMS voltage will be this RMS of this one, and the RMS will be the same. This will be the Vm, simply that Vs, whatever the supply voltage was, the Vrms of the output voltage will be Vm by root 2. This will be the RMS value. This is like, doesn't matter whether it's a positive and negative, or positive and positive is the same, because root mean square value is the same. Once you know that, we can find out the average value of this rectifier. Now, what is the average current of this rectifier? It is asking for you. It is asking for you that this is one example. Ask for you if the Vm is 10 and the R is 2, the average diode current will be that. You can calculate it out. Once you know the output voltage, you know the average output voltage of this output rectifier, you know the resistance, and you know the Vm. You should be able to find out what is this, the current, what will be the average diode, the current. But by the way, the average current of the diode, this will be this is the average current, is a 10 here. If this is a 10 here, this will be average current from here. From here, it will be 2 of them, right? It will be 2 of them. This will be 10 divided by 5. This will be 5. The average current will be shared by the 2 diodes. It will be like this will be shared by 2 diodes. This will be, keep in mind that this is the average of the output voltage, output current is shared by the 2 of them. And this will be half of them. Like, what is this one? I think the average at the diode current of the rectifier, this is the average diode current of the rectifier. I think it's the same example before that. This is the Vs is 20, and then R, and the average diode current will be the same one. I think it's the repetition of the same problem. But this is the RMS diode current. What will be the RMS diode current? The RMS voltage will be whatever this Vm, if this is the Vm there, the RMS voltage will be Vm by square root of root 2, and then the divided by R, this will give you the RMS current. Now, there's the question, be careful about if the RMS current here, RMS current, if this is the IO is the RMS current of this output is say 10. If this is the output, say for example 10 A, now what is the RMS of this current here? Okay, what is the RMS of the diode current? It will not be half. It will be the diode RMS of that one, of this diode 1, will be 10 divided by square root of 2. This will be half of the time. It will be half of the time, and that will be not a half. It will be square root of half. Okay. The RMS value, when the RMS value is shared, it is shared by the square root of time. How do I know that? How do I know that? If this is the 10, this will be I know that RMS of that one, diode 1 square, RMS of the diode 2 is square will be equal to RMS of that total. Now square of that, if you got this one, it will be 10 square divided by 2, 10 square divided by 2. This will be the one. If you can do that, this will be what? Half and half, 10 to the first square. That will be 10. Okay, we got this square. 10 square, the RMS square equal to 10 square. That means RMS equal to 10. The RMS value, if you are looking for the RMS, you cannot add them. This will be if this will be RMS current will be shared by whatever the current divided by 2. There are 2 of them. If there are 3, it will be shared by 3. Now ripple frequency, this one there are in a frequency of the whole fundamental cycle. This is in one period. There are two pulses. There are two pulses there. That means the frequency of that pulse will be equal to 2 fs. The ripple frequency of that will be 2 pulses. Now the output voltage of the full wave rectifier is basically the same we mentioned to you before. The RMS value of the waveform from these two half sine wave, this is the plus and minus, is the root mean square, root of the mean of the square. This is the root of the voltage VO square into dt, root of this mean of the square, and then when you make a square of that, doesn't matter positive or negative, that will be Vm by square root of 2. Okay, this is what we expect in a normal sine wave to the peak value to the RMS value. The input current of a rectifier, if you're looking for the input current, what is happening to the input current? Look at the input current, we are looking the input side. Like if this is an ideal transformer, if this is a half sine wave, that will be a half sine wave too. Okay, if this is a sine voltage, a sine current here, it's following opposite direction, there will be another sine current coming on the other side too. That means if this is an ideal transformer, if the output is like output current is like this, but the transformer side, one is going this way, another one going that way. Like if I look to the input side, this will be basically a sine wave. But although in real life, because of the normal of this transformer, what you call nonlinearity, it will not be pure sine wave, it will be distorted type of sine wave. Like peak load current, the peak load current, what it says, like what the question says, the peak current with an RL load will occur at delayed after the peak supply voltage. Like you know that if you got an RLN, it is a power factor that, if you got a power factor is the angle, and the angle is a tan inverse omega L by R. This is the impedance angle. Like that means that angle will be the inductor. It will be inductor always come at the later than the voltage. This will be delayed. The delayed after the peak voltage. Whatever the peak happens, the peak will not happen at the same time. It will be delayed for an inductive load. The battery voltage, if there is a battery here, what will happen? The battery, increasing the battery voltage will make the load current discontinuous, because more towards discontinuity. If you think about it that if this is if you got a half wave, if you got a half wave, if you got a battery there, that no current can flow, the current only can flow when that this is greater than the battery. If this is a battery, the current can flow only during this interval of time, only when that the voltage, the input voltage is greater than that. As you can see that if you increase the battery voltage to 0, you get a maximum. The current will be more continuous. If you make this, the battery is more and more on the more going up, it will be going towards the discontinuity, more towards the discontinuity. If you increase the battery, it will be more towards the discontinuity. The waveform of that, there's a things you need to look for. If the voltage is if the load is very highly inductive, that means that if this is very highly inductive, the current on the output side, the current will be almost like a constant. But there are two diodes, one is a positive and a negative, and then they are going to switch. One will be positive. When there is a positive, this will be positive, and then the negative there. Now what we expect on the input side will be like, if you input side, you're going to see the current is changing from, it's like a square wave. But in real life, because of the inductor will not be infinity, there will be some ripple there. But in any case, that input current will be a square wave basically, and that square wave, that will be the displacement angle. This is the displacement angle will be that is the displacement determine that. Now how do you find the power factor? In this particular case, it will depend on the fundamental component of the input current, which will be, if you do the Fourier series of that, this will be fundamental component of the input current. divided by the RMS of this one. What is the RMS value of their square wave? It's simply an RMS value, because if you take this one plus of that one and that one square of that, this is the square, and dt and 1 over t, and then 0 to t and square root of that, it will become kind of like is. That the RMS value of a square wave, which will be simply the current itself. Now what I'm saying now, if you have this waveform distorted like a square wave distorted, the only way you can find the power factor by finding the fundamental component of this waveform, the current divided by the total current, and the displacement angle is not the power factor angle of the load angle. The highly inductive load, let us take a highly inductive load. This rectifier is supplying a DC motor when the load is pretty much constant. This will be like, in this case particularly, if you look to the input side, it will be like a half wave and half wave. There will be ripple there. There will be ripple there. If you assume this is ripple free, or almost like ripple free, then you can say that this will be like a square wave. And the fundamental component will be a sine wave. It will pass through there, and as a result, the RMS value of that highly inductive load. What is the RMS value? It will be the same thing. The RMS value of this waveform of the square wave is simply IA. Like if you look to the highly inductive load, they're asking for the input current of this, well, the highly inductive load is also IA. Whatever the input current, this is the input current here, will be log. If you look to the input current, it will be like a positive and negative, and that the input current is RMS value is still the IA. The load is IA, and then our input is also IA. The power factor, the power factor will be basically, there is an example in the book. It shows that the power factor for a highly inductive load, especially inductive load, is a point light lagging. If there is a capacitor, it will be leading, but for inductive, it's normally lagging there. It will be about 0.9. You can see the power factor is pretty much constant with the highly inductive load is like a 0.9. And the total harmonic distortion of this waveform is shown in a highly less than 5%. You can show there is an example in the book. It shows some derivation of that, finding the Fourier series of that of this particular waveform. It shows that total harmonic distortion will be less than 5%. It's about 48%. You can check that, the expression there. Please check it. And the highly inductive load, what is asking for? If the load current is shown in highly inductive ripple free, the RMS value of each diode current. Now that's the question. RMS value. This is the RMS value here is IA. What is the RMS value of each diode current? Remember, it is RMS value is divided by 2, shared by 2 devices, D1 and D3. That means that will be IA divided by square root of 2. That's what it is. The answer is. If it is shared by, if a current is shared by n number of devices, the average current, if the total average current, say IA, it is shared by n devices, it will divide by IA divided by n. If it is the RMS value is IA or 10M, it is shared by like n devices, it will be IA divided by square root of n. This will be IA divided by n. This is for average, this is for RMS. Since there will be 2 devices, there will be a square root of 2. What it says that the average value of each diode current, like in this particular case, the average is the fixed, IA is the fixed. The average will be equal to divided by 2. This will be IA divided by 2. This will be IA divided by 2. Each will be divided by IA by 2. This is the basic. Remember that. Now we have covered this full wave rectifier. If this is a half wave rectifier, this is not in the book, but you have covered them in electronic circuit. But everything will be half. Whatever the voltage you have, that in the electronic circuit, and the same will apply. What it says that for ideal transformer, the input current of the cell will be pulsating wave. Like if this current here is like out, the current here will be like half pulse, because the half pulse will not be there. If this is your input, the output current, like this load current, this current will be also will be like this. That means this is a pulsating. It's not a it's not the AC, it's a pulsating DC. That input current is a pulsating DC. I should mention that sometimes it's confusing there. Now, what is the AC? If you have a waveform, something like the 0 to with an alternating current, it will be with respect to 0, it will have a positive value and a negative value. There will be a positive value, negative value. But if this is an alternating current, if there is a DC, there will be pulsating. There will be pulsating there, and then 0 here. All the current is always a positive. If you put an emitter, in this particular case, current will go in one direction and the current will go in the opposite direction. But in this particular case, because it never go less than a 0, the current will be fluctuating, but all the time the current will be unidirectional. This will be DC. It's called the pulsating DC. It's not a pure DC. Pure DC will be like this. The answer is pulsating DC. The half-wave rectifier, what is this? The supply, the ripple frequency will be FS, because there will be only one pulse. Okay, there will be one pulse frequency. If the supply is the FS, that will be 1F. The half-wave rectifier is asking you the average current of the rectifier. You can find out the average voltage will be equal to Vm by 2. Vm by the 2 is that Bm by pi. Bm by pi is the average, the voltage of the diode. Average voltage of the diode. Now rectifier is Bm by pi. For full wave rectifier is 2 Vm by pi. But in this case, it will be not a 2-1. You can find out the voltage. Once you find the voltage, you can find divided by the resistance. Going to find the current. Please check that one. And then this is the RMS value of the rectifier. Now the RMS value of that half-wave rectifier will be, how much is that? RMS will be equal to, this is the Vm, the Vm by square root of root 2. You can find out the RMS value of the half sine wave. No, sorry, this is not a Vm by square, Vm by 2. Vm by 2, because it's only half of it. Vm by 2, the RMS value will be Vm by 2. If this is the Vm by 2, you can find out the current. Once you find the RMS current, voltage divided by resistance, you can do RMS current. You should be able to calculate that. Now, RMS value of this, and we just mentioned to the RMS value of them is Vm by 2. The RMS value of, if you see a waveform like this, now this will be the RMS value of this, the half sine wave is Vm by 2. But in the previous calculation, you do some calculation. This is the application of that one. Like in three-phase rectifier, you're going to have, look at that. If you got this highly inductive load, you got this output average current will be shared by 3 of them, and the RMS current will be shared by 3 of them. And that's to keep in mind that this is the three-phase rectifier. There will be on the top there are 3, there are bottom in the 3, but look at that. The pair it looks for 360 degree D1 and D2 is in one pair, D2, D3, D3, D4, D4, D5, D5, D6, D6, D1. There will be 6 combination of them, 6 of them. In a 360 degree, there are 6 of them. Each pair will be conduct from 60 degree. That means that on the top one, each of them will conduct for D1 will conduct 120 degree, and then the bottom, each of them conduct 1 degree, but each one is shifted by shifted by 120 degrees, shifted there. Okay, just to keep in mind, each diode will conduct from 120 degree, and just to keep in mind. Okay, we'll come in a minute. Now this is the waveform. We expect that you can see that this is the output voltage. This is the output voltage, and then the line current. The line current of that, each line current will look like, if you say ripple free, if this is the ripple free, this will be the ripple free. Okay, this will be the ripple free. This will be the ripple free. Okay, that's on. But if you look to the diode current, this will be diode current. If you want to find the average diode current, you can find out what is the average will be between that. You need to find the average within the whole cycle, be constant 3 pi by pi. This will be 3. This will be the IA. Will be average of that over a period of 2 pi. This will be pi by 3 2 say 2 pi, okay, 2 pi, it's a 1 period, and the dt, you can find the average. If you want to find the RMS of that, you make a square root of that, and then take a square root. That's finding that one. Just keep in mind that when you do that, you assume that uh, this waveform, this is between here, the RMS, the line current will be, line current will be opposite of that one. This is to look for. There are some equation in the book. Like if you're looking for, asking for that, if the frequency of that supply with the ripple current will be how many times? There will be 6 pulses. There will be 6 pulses. We ask for what? If this F is the supply frequency, the frequency output ripple, there will be 6 bumps. There will be 6 ripple there. There are 6 times, 6 of them. That means 6 times of that supply, okay? That means you will be here, not Fs, 2s, 3s, it will be 6 times. There will be none of them. This, the answer is none of them. Now, that's asking for that. If you want to find out the average, you can do like 0 to pi, and you can find that this is the 3 square root of 3 pi Vm is the peak value. And they ask you, the question asks you, this, the Vm, the R, they are asking you the average current of that, the average diode current. Like whatever you found, the average current you found at 10, or IA is equal to 10, each diode will be carrying divided by 3 here. It will be divided by 1, 2, 3, it will be 3. Each diode current will be 10 divided by 3. That's basically, you do the calculation, you find it out. Maybe one of them, maybe none of them. Okay. 3-phase rectifier. Now, if you want to find the RMS value of this one, this is the RMS value, is slightly higher than the average value. They ask you the same question. The RMS value of this, the current of the RMS diode current will be whatever that. If this is the RMS diode current, remember that once you find this, the RMS voltage divided by the resistance, you got RMS current divided by what? 1, 2, 3. It will be the RMS of that IO divided by square root of 3. Remember that it's an RMS value. When you divide by RMS value, it will be square root of that 3. Okay, keep this in mind. Now this waveform has this. This waveform has that. This is the. Remember, each one is conduct from 120 degree, and then 120 degree, and then this 120 degree 0, and then 120 degree over a period. Okay, like you see that this I is 0, 120 degree, 0, 120 degree. 0 for 120 degree there, this is the waveform always goes there, and it's a negative other one. They ask you the questions, they integrate that value. The RMS value of the input phase current, like input. If you look to the RMS value of them, if you assume that basic say it's a square, right? It's a square of them. What is this one? If you do that, the RMS value, basically simple like this. You look through that. You look through that, pi to pi. There are, you look through that, you got IA square dt 0 to, let's say, pi by 3. There are pi by 3 to pi, pi by 3 to pi divided by 2 pi. Then remember, there are, one is a positive and a negative. Over a cycle, there will be 2 there, and square root of that. If you do that, you're going to find out this will be IA equal to square, IA equal to IA 2 by 3 square root of 3. Okay, there will be 2 of them. Okay, because at 2 by IA 2 by 3, this will be the RMS value of the input, the current. Okay, this is the ask you the similar question. Ask you assuming this one, assuming the load current is this is the negligible RMS value of each diode current. Okay, you are looking for whatever the IA was that. This is the IA of that, right? It's the IA of that. Each diode current will be, because remember, this is for 1, this is the another one, 120 degree from 1, another from 120 degree, another from 120 degree, another from 120 degree. If you have the output is a continuous, okay, continuous, the one is for, this is for the diode 1, this is for the diode 2 shared, this is diode 3 shared. That means the average current of that diode will be equal to RMS value. So the RMS value of the diode current will be IA by square root of 3. This will be square root of 3. Okay, there are 3 of them. It's shared by the 3 of them. I think that's the end of the chapter. Please review them, and also there is a, I believe there is a video on that, on this the RMS values, the RMS values, how to calculate the RMS values of different waveforms. Please review that video too. I think that's the end of this video, and thank you.